Thank you, Don, and welcome everybody. Welcome to this year's Sagan workshop, Imaging Planets and Disks. As Don mentioned, the workshop is hosted by the NASA Exoplanet Science Institute, NEXI, here at Caltech, which is itself an important part of the NASA Exoplanet Exploration Program, which I have the privilege of managing and about which I'd like to say a few words to you today. Now, for many of you, this is your first visit to Caltech, or maybe even your first visit to California. So I thought I'd start off with a map and put things in context. So here we are at the Beckman Auditorium at Caltech on California and Wilson. Here's where I work. I work at the NASA Jet Propulsion Laboratory, 7 miles away in the foothills of the San Gabriels. One of the things JPL was first known for was the launch of the first U.S. satellite, Explorer-1, which discovered the Van Allen radiation belts. More recently, JPL is known for dramatic and nail-biting landings of rovers on Mars, followed by exuberant celebrations in mission control. But in the 1980s, when I was at a point in my career not too different from where some of you are today, JPL was known for the Voyager spacecraft, which were busy exploring the outer solar system. And in 1990, NASA commanded the spacecraft at the request of Carl Sagan to turn around and take a picture of the Earth from a distance of 4 billion miles, producing the image that we all now know today as the pale blue dot image of the Earth. And yes, you are here too. And in 1990, this image was both beautiful and sobering in its visual impact. And 24 years later, it reminds us that to the rest of the universe, the Earth is just another exoplanet. And that brings us to our work here this week, Imaging Planets and Disks. Looking around the room and seeing the faces in this room and the assembled expertise, I'm reasonably sure that some of you, many of you, will be involved in finding and characterizing and searching for signs of life on a pale blue dot around a nearby star. The dream of that actually happening is what motivates me to come to work every day, and I'm pretty sure it motivates a lot of you too. Let me tell you a little bit about the program. So the NASA Exoplanet Exploration Program is a part of NASA Astrophysics Division. We are chartered and responsible to NASA Astrophysics and to the community for helping to implement NASA's space science implementation, focusing on exoplanets. Now, not every exoplanet mission or all exoplanet science is part of the program, but a lot of the important work is. Let me tell you about some of it. Many of you are familiar with the Kepler mission. That's part of the EXEP program. Now it's in closeout, processing the last 4 years of the data, all the way from Q1 through 17, to draw out the planetary statistics. Also now the K2 mission, that little spacecraft now with just 2 wheels, observing in the ecliptic plane. It's in campaign 1 right now and accepting proposals from the community for the later campaigns. The W-FIRST AFTA mission, a mission envisioned for dark energy infrared survey, microlensing, and also an internal coronagraph for exoplanet direct imaging. Probe scale missions, an external occulter, and a coronagraph. These are all studies that are part of the Exoplanet Exploration Program. The program also involves important precursor science, the Large Binocular Telescope Interferometer managed by the University of Arizona. Its purpose is to detect and characterize exozodiacal light around nearby stars for the purpose of constraining the mission design of future exo-Earth missions. The program also manages 1/6 the NASA time, the 1/6 of the time on the Keck single apertures, some of which is used for precision radio velocity follow-up of the promising Kepler candidates. Now, to make all these missions possible, the program manages and works with the community, many of you in the room actually, a vibrant technology development program for high contrast imaging, both for internal chronographs and external occulters. We include have a pretty vibrant public engagement policy program, as well as the program contains the NASA Exoplanet Science Institute, which is hosting this exciting workshop. This graphic depicts the arc of exoplanet missions leading from where we are today to the future envisioned at the last decadal survey. That future envisioned leads through a future mission of W-FIRST AFTA, leading towards a New Worlds telescope, that ultimate New Worlds telescope, one capable of detecting, characterizing, and looking for signs of life around on planets around our nearest stars. These missions accomplish planetary demographics. The Kepler spacecraft and the upcoming TESS mission with precision radio velocity follow-up from the ground. Other missions will be involved in characterizing the exoplanets for the first time. The Hubble and Spitzer telescopes, never envisioned at their time of launch for conducting exoplanet characterization, nevertheless do so, based in large part due to the creativity of people like you in this room. The James Webb Space Telescope will follow up test targets for precision transit spectroscopy. Looking ahead, the W-FIRST AFTA mission will perform both demographics through the microlensing survey, completing the census begun by Kepler, as well as do, for the first time, do direct imaging of cool giant planets and ice giant planets. And ultimately, the New Worlds telescope, which would follow that, following the next decadal survey, will be the one that at least we hope will be part of the detection, characterization, and search for signs of life around the pale blue dots. Now, when we add the missions that are being conducted by our colleagues in Europe, ESA, CNES, we see the picture starting to get very crowded. And I find this very exciting because that reminds us what an exciting future we have and how so many people around the world are being drawn into this field of exoplanets and the search for signs of life. So when I see this, I'm reminded about what an exciting field this is and what a great time it is to be working on exoplanets. When we look at the missions that we have underway, both in the program, elsewhere at NASA and ESA, you see that we have a certain amount of activity currently in Kepler, K2, HST, and Spitzer. Gaia is now on orbit for astrometry. And we have activities underway in studies for the W-FIRST AFTA mission and the two probe studies, as well as technology development, leading towards mission concept reports in January of 2015. Upcoming, we have other missions coming online. In particular, Large Binocular Telescope Interferometer will commission in April of next year and begin a survey of 50 nearby stars to determine exozodiacal light. Now, NASA Astrophysics envisions W-FIRST AFTA as the next strategic mission for the Astrophysics Division, leading to a new mission start in 2017 with a launch readiness date in 2024. Now, to make that happen, there's a significant amount of technology development that's underway in the high contrast imaging, the post-processing, the wavefront sensing and control, deformable mirrors. Many of you are involved in that and are the subjects of this week's work. The two probe studies are imagined as potential alternatives to W-FIRST AFTA should it not emerge as the next strategic mission. But even if they don't, they serve to motivate the technology investments for the last half of the decade, leading to mission concept consideration for the New Worlds telescope in 2020. There's a lot of work going on right now, particularly in W-FIRST AFTA. This is a mission that's managed by the Goddard Space Flight Center, and the coronagraph instrument is managed by JPL. And this mission involves a visible coronagraph that uses deformable mirrors, wavefront sensing and control, hybrid LEO masks, shaped pupil masks, to draw out a planet around the nearest stars at a level of contrast 10 to the minus 9 or better relative to the host star and at inner working angles of a couple hundred milliarcseconds. That's pretty tight. And this is possible in large part because of the work that many of you in this room have done over the last 10 years. When this is made to work, this mission will be capable of characterizing over a dozen of our known radio velocity giant planets and be capable of detecting and characterizing more than a dozen more planets waiting to be discovered around these nearby systems that we feel must be there. Here's an image of the instrument as it's being designed at JPL. You can see it here, how it would be packaged beneath the 2.4 meter diameter mirror right next to the wide field instrument. This wide field instrument also will perform the microlensing demographic survey of planets largely beyond the ice line, largely beyond the snow line, through the technique of microlensing, completing that census begun by Kepler. The two probe studies that are under consideration, one is the internal coronagraph and the other is the external occulter. XOC, as we call it, is led by a science definition team led by Carl Stoppelfeld at the Goddard Space Flight Center, and XOS, as we nickname the Starshade, led by Sarah Seeger of MIT. These two missions they're really a challenge by NASA headquarters to find a compelling and viable mission set that's capable of performing science that can't be done from the ground in the 2020s for a cost of $1 billion or less. So these teams are busy working right now. You can see their interim reports on our website. XOC would be capable of, with a 1.4 meter diameter mirror in an Earth trailing orbit, capable of the kind of science that the W1 mission is capable of. This spacecraft is modeled after the spacecraft of the Kepler spacecraft. It's an off-axis telescope. The formation flying external occulter envisions a 34-meter starshade about 37,000 kilometers away. And because of the ability to see to small inner working angles, possibly 20 exoplanetary systems are accessible in their habitable zone, which may be able to, and this mission may be able to detect the possibility of exo-Earths in those systems, depending on the assumptions of the performance of the spacecraft and the instrument for the high contrast imaging and the presence of exozodiacal light. These are all very exciting missions. Here's the concept of the Starshade, showing the principle of operation and its ability to get into a small inner working angle by decoupling the inner working angle from the size of the telescope and the aperture size. The inner working angle is now not a function of the lambda over d of the telescope, but of the diameter of the starshade over the distance to the starshade. This would be an Earth leading orbit. So some of the complications of the wavefront sensing and control and the precision control of the optics and the masks inside the telescope are removed by this. On the other hand, the challenge now for the external occulter is the lateral sensing and control of the spacecraft relative to the starshade over large distances and the repositioning. So I invite each of you to read more about the technology development that's underway. There's a tremendous amount going on. The studies that we have in the Exoplanet Exploration Program at our website, exop.jpl.nasa.gov. And I'll just end with this slide, which reminds us of our exciting future, our very exciting present. And I'd like to invite each of you to get to know one another in this workshop, because by speaking with one another, you will almost certainly be speaking to somebody else who will be involved in their lifetime, in their career, in the detection and characterization and the search for signs of life around an exo-Earth. And then I want you to believe that that's true because the person is you. And it's because of what you do over the next few years. It's because of what you do this week and what you learn this week. So with that, I'll say thank you and accept any questions.